Okay, hello, my name is Patryk, and this is my presentation on the conference CART 2024. Thank you for being here, thank you for watching. It's a great opportunity for me. So today I would like to talk about the connection between combinatorics and dynamics through fixed point indices of iterates. Let me start with a short outline of this presentation. So as you can see, I divided this presentation into three different parts. So at the beginning, I would like to talk about the motivations. Also, I want to show you all the necessary definitions that you need to know to understand the whole concept of this theory. Then I will talk about the fixed point indices of iterates, and in particular, I will talk only about their combinatorial properties, such as the modulo P property, dot relations, or periodic expansion. Then I will pose the main problem in various classes of mobs, and of course I will show you some known results in those classes. And at the end I will talk about the recent result that I obtained with my advisor Professor Graf in the class of orientation reversing homomorphisms. So I hope you will enjoy this presentation, and let me start with the motivation. So let F be a self-map of Rm and X0 be an isolated fixed point of F. Then we can ask a very interesting and natural question. What are all the possible dynamics of F near the fixed point with respect to the fixed homotopy? And the fixed homotopy is just the standard homotopy with one additional assumption that the fixed point set is compact at any time of this homotopy. So, of course, we can ask this question in different classes of maps, but there are four natural classes to study. So we can assume that F is a continuous map or homomorphism, orientation preserving or orientation reversing, a smooth map or diffeomorphism. And the other question is how we want to study this possible dynamics, and we want to study these dynamics using the topological invariant, the fixed homotopy class, and this invariant is just the fixed point index of a map. So let me quickly define it for you. So for simplicity, I will only consider the self-maps of the plane, because on the plane we have a very nice geometrical interpretation of this invariant. So we have a map F and X0 an isolated fixed point of this map. And because X0 is an isolated fixed point, then it has of course an open neighborhood, and we can choose this neighborhood as an open ball with the center at the point X0 and the radius R. And then the fixed point index is just defined as the topological degree of the associated map phi, where phi is a self-map of the boundary of this neighborhood, given by the formula radius times x minus f of x divided by its norm plus x0. And for those of you who don't remember how to compute the topological degree, in this case, it's pretty easy, because all you need to do is to consider the induced homomorphism on the first homology group, and because the boundary of this neighborhood is just a circle, then we note that the first homology group is isomorphic to the group of integers, and then it's easy to see that the generator of this group is need to be transformed onto itself, multiplied by some integer, and this integer is just the topological degree. Sometimes it is also called the wrapping number of a map. So for the particular example, if our map has an analytical expression, then the fixed point index is just a multiplicity of the zero of the function z minus f of z. Also, I want to show you a more geometrical way to calculate the fixed point index, and it is possible for the flows. So let us consider the planar flow psi with a singularity at the point x0. Then the fixed point index of the time one map of such flow is equal to the 1 minus the number of the hyperbolic sectors around the point x0 divided by 2 plus the number of elliptic sectors around the point x0 divided by 2. And for the example, you can consider the bottom left flow from the drawing that I made, and it's easy to calculate that the index in this case is going to be 1 plus 4 over 2, so it's going to be 3. Okay, so what we can do now? Now we can assume that x0 is an isolated fixed point for each iterate of f. Then the fixed point index of such iterate is also well-defined integer. And now we can ask another question. what are all the possible sequences, and why this question is even interesting. Now, first of all, because the knowledge about the entire sequence of indices contains much more information about the dynamics near a fixed point than just the fixed point index of the first iterate. And of course, the answer depends on the class of maps that we are considering, and today I will show you two results. First one in the class of continuous maps and the second one in the class of homomorphisms, and I will show you the differences between these two results. And of course, we are going to consider these maps on the plane. So there is also another question. What are the restrictions on this sequence? And it turns out that this sequence cannot take arbitrary values, but its element must satisfy some congruences. And the first congruence that I wanted to show you is the modulo P property, and it was discovered by Krasnoshelsky and Zabrejko in 1971. They observed that this congruence is satisfied for each prime number P, and this is interesting because it looks exactly the same like the congruence from the Little Fermat's theorem, right? It was proved by Steinlein 1 year later in 1972, but there is more general restriction on this sequence than this, and it was found by Albrecht Doll in 1984, and he proved that for each natural number f we have the following congruence, where mi is just the arithmetical Mobius function, and for those of you who don't remember the definition of this map, it's pretty easy because uh, this map is defined by the three following properties. Mi of 1 is equal to 1, mi of n is equal to the minus 1 to the power of r if n is a product of r distinct primes, and it's always 0 otherwise. So with this function is connected a very interesting formula, and this is a Mobius inversion formula. The Mobius inversion formula states that if we have a close relation between these two sequences, then this relation needs to be satisfied. And we can use this formula for our sequences of fixed point indices, because first of all, let us define the coefficients an, and we are going to call them Dold coefficients. They are equal just to 1 over n times this whole sum, and we know from the Dold congruences that they are always integers. And then we can multiply both sides by n, and we will get this equation on the right side of the implication. And now we can put the Mobius inversion formula to the right side of it, and we will get the representation of the fixed point indices as the following sum. And now we want to represent the fixed point indices even more general. So we can do that, but we need to define first the Kef regular sequence. Sorry. So the Kef regular sequence is defined as the periodic sequence of 0 and k, where the non-zero elements appear only for the indices of the sequence that are divided by k. So this is just a sequence 0, 0, 0, k, 0, 0, 0, k, etc. So now we have this periodic expansion theorem, and it states that the sequence of fixed point indices can be written uniquely in the following form. So in this form you have the regular sequences and the Dold's coefficients, right? So okay, let me show you some example. For example, if we have the sequence 117, 117, etc., this sequence can be represented as rec1 plus 2 rec3, because if the indices of the sequence are not divided by 3, then rec3 is always 0, and then you have rec1, and otherwise rec3 will appear, and then you will have rec1 plus 2 rec3, so 7. Okay, So now we have, now we can reformulate the main problem. So if we have an arbitrary sequence of integers, is it possible to find a self-map of the space Rm such that this equality is satisfied? Um, this is a non-trivial problem, but I will try to show you some answers. And it's also important to know that for the particular n, for example, n0, this series is always a finite sum, because for k greater than n0, rec k of n0 is always going to be 0. So the first result that I wanted to show you is the result of Graf and Nowak-Przygotsky from 2003. They proved that for arbitrary sequence of integers, there exists a continuous self-map of the plane such that the equality is satisfied. So basically it means that the only restriction in this class for the fixed point indices of iterates, the only restriction is the dot relation. So it's hard to say about the dynamics right here, but for the class of homomorphisms, it's completely different case, because Ruiz del Portal and Salazar in 2010 proved that all possible forms of fixed point indices in the class of plane homomorphisms are given by this short sum rec1 plus ad rec d. And of course the hardest part here is to prove that there are no other possibilities, but also it's interesting how to realize this sum, and I will show you that shortly right now. So let us define a planar flow Cp as the flow whose phase portrait around the point x0 consists of 2 times 1 minus p hyperbolic sectors for p less than 1, 2 times p minus 1 elliptic sectors for p greater than 1, and a source or a sink, it doesn't matter at this point, for p equal to 1. Okay, so we have that, and then by the Poincaré-Bendixson formula, we get that the fixed point index of the time one map of such flow at the point x0 is always going to be p for each iterate. What we can do now? For a given integer d greater than 0, we can define the planar rotation map O by an angle 2p over d around the point x0, and for a d, an arbitrary integer, we can put p of the form 1 plus ad times d, and then the maps O and HP commute. And basically it means that the elliptic sectors are transformed onto the elliptic sectors by the rotation. Hyperbolic sectors are transformed onto hyperbolic sectors, and also on the axis the sinks are transformed onto the sinks, and the sources are transformed onto the sources. So now we can calculate the fixed point indices of this map, of this composition of maps. So we are going to have the result 1 plus ad times d if n is divided by d and 1 otherwise. And why is that? So the first case is pretty easy, because if n is divided by d, then the rotation is going to be identity. So then you have only the influence of the flow, and because we showed that the fixed point index of the flow of the time one map of the flow is going to be p, and we chose p as the 1 plus d ad, then we have the result. But otherwise is 1. And why is that? And this is because the influence of the rotation um, make that this composition is going to be fixed homotopy to the sink. And this is a pretty nice exercise to do, so I will leave you with that. But as you know, sink is going to have the index equal to 1, so that is going to be 1 otherwise. and thus this result we can write with the periodic expansion as rec1 plus ad rec d. And we realized these results even in the class of diffeomorphism. In the higher dimensional cases, it's not true that you can realize homomorphisms and diffeomorphisms in the same way. So it's also interesting on the plane. Okay, so now I want to talk about the motivation to my work. So in 2013, Hernandez, Corbato, Lecalves, and Ruiz del Porzal, they proved that if F is an orientation reversing R3 homomorphism with X0 isolated as an invariant set, then the equality can be satisfied if and only if there are only finitely many non-zero AK and A1 is less or equal than 1 and AK is less or equal than 0 for all of k greater than 1. And this basically means that the sequence of fixed point indices is periodic. This is the first point that says that tell us that. And what means that X0 is isolated as an invariant set? This is the definition, but basically it means that the trajectory in the neighborhood of the point x0 needs to escape in positive or negative time. So for example, if you consider the hyperbolic sectors around the point x0, then it's going to be isolated as an invariant set. But if you are going to consider only the elliptic sectors around the point x0, then it's not isolated as an invariant set because they will never escape some neighborhoods. So me and my advisor, Professor Graf, we were curious about the situation when the set x0 is not necessarily isolated as an invariant set, and we get a very interesting result because we we proved that for any given sequence of integers there exists an orientation reversing Rm homomorphism. So not only in the three-dimensional case, but we proved that in general, such that we realized this series as a fixed point indices of iterates. So if you are interested in our work, then you can, and you are interested how we did that, you can check our preprint on arXiv under the title Fixed Point Indices of Iterates of Orientation Reversing Homomorphisms. And I think that I don't have any time left, so this is references, and thank you for your time.